Let us start lecture 53. The course is on phase diagrams in single component and binary systems, and the topic what we will discuss is on enthalpy of mixing and Gibbs free energy of mixing when a solution deviates from ideality. In fact, we have been discussing this for the last couple of lectures, and today what we will see that when we have a situation like del H mix is very large positive quantity, what will be the phases that should be stable in a system. We will try to look into that part. In fact, couple of important aspects we have learnt. One is there will be two convex downward portion of del G mix and one convex upward portion in that particular del G mix versus x b or the composition plot when del H mix is large positive, that we have learned. And also we have learned that when del H mix is very large, okay, that means omega is extremely large quantity, but finite quantity. That case also we will always find a small dip at both extreme ends of compositions. That means, there will be always a two convex downward portion, whatever be the tininess of that particular portion, but that should be there because and that then it will be followed by the slope change and it would become the curve would become convex upward. Okay. That is that is what we have learnt, and why it happens, because at extreme ends when the composition becomes that the solution becomes infinitely dilute or we can say the solute content tends to 0, then the Gibbs free energy change with composition, that slope becomes negative infinity. So, the system ultra pure material or metal would always try to accept solute atom, so that the free energy of the system goes negative infinity, and that way the solution formation is extremely spontaneous. That is what we have learnt. And second part what we have learnt is there will be inflection points, and we have seen how the inflection points, two inflection points appear in the plot of del G mix versus x b when del H mix is extremely positive or very large value. Okay. And now we will try to see what are the phases that will be stable in a system when we have large positive del H mix. Now, if we have, so in fact, what we have done, we have used regular solution model we have applied it to a binary system A and B, where x A and x B are the mole fractions, and we are making 1 mole of solution. Fine. And remember, we are keeping temperature and pressure constant. Pressure is 1 atmosphere. Fine. So, and we have taken 4 cases, case 1, case 2, case 3 and case 4, where case 1 omega equal to 0, del H mix equal to 0, case 2 omega is less than 0, del H mix is less than 0, here omega is greater than 0 and del H mix is also greater than 0. And here when I am writing my negative value of del H mix, it is a small negative. Similarly, in case 3 it is small positive, and case 4 omega greater than 0 and del H mix greater than 0. So, that means it is a large positive. And in these 3 cases we have seen the plot free energy composition or delta H delta G mix versus composition plot. If you recall, this is 0 0, x b equal to 1, x a equal to 1 and x b is varying this way. So, all three cases, this should be the case 3. Then we have case 1 and the third one is case 2. Fine. We have already seen this and we have understood why it happens. Now, in all three cases we have seen that even whatever if we take two arbitrary compositions, let us say on this particular plot we have taken two arbitrary composition and we have shown that if we take equal proportion of these two composition solution, let us say this is A and B. So, there will be a point on this particular line C and that C, if we take a vertical line from C, it will be the minimum point on that particular delta G mix versus X B plot, and here it is delta G mix plot. So, if we mix this composition the solution of composition B and solution of composition A, they will mix spontaneously and form a single phase homogeneous solution, which will be decided by the minimum point on delta G mix versus X B plot, and this composition would be 0.5 X B equal to 0.5. We have learnt that, and in fact, all three cases we will always see any arbitrary composition if we take which is across the midpoint of delta G mix plot, we will see that there will be homogeneous solution that will form of a single composition. Okay. So, for example, in this case the composition would be here, here it will be at this point. So, like that way all those composition will form. So, it is a kind of homogeneous single phase solution would come out if we mix two different composition solution because of the lowering of free energy. So, here you see the delta G is equal to negative. Similarly, all cases delta G is equal to negative, here also delta G equal to negative. So, this all cases they are spontaneous. Homogeneous single phase will come out. Okay. But the case 4 we have to understand. In order to understand case 4, let us see the situation here. Okay. This is 0 0, x b equal to 1, x b equal to 0, let us say. This way x b is increasing. So, my plot would be like this, and we see there are a couple of points. Let me just mark those points. Let us say this is A, this is B, this is let us say C, and this is D. This one, this one, this one, and this one. Right? Okay. And inflection point we can get two inflection point. One would be here, another would be here. So, there we can have delta G mix equal to 0, these two location. Okay. So, those are spinodal point. Fine. So, let us start from A. Okay. from A, this is the plot we are talking about, case 4, we are discussing case 4 now. Let us say I am starting with A point and gradually going towards B. So, if I A and B part, if I draw it, if I zoom it, the zoom portion would look like this. Okay. So, let us say this is A, this is B. Now, any composition in between A and B, if I take any solution. So, for example, let me take this composition. Okay. I mix two metals A and B and form a composition like this, and now I see what will be the phase that would form. In fact, this entire line talks about the free energy of a particular phase. Now, when it comes here, we see that this would be, when I talk about this particular plot, this plot actually indicates the homogeneous solution when it forms, what will be the change in free energy as we change the composition. Now, here if I take that, let us say two ways we can go, either we can go upward or we can go downward, fine. Now, if I go upward, so let us say if I go upward, so I can go to this level, but if I see, so then there could be a possibility of distributing into these two composition solutions, but that is impossible. So, this process is impossible. Why? Because delta G is equal to positive, okay, non-spontaneous. So, then we have to see whether this particular point has any line or any point in the free energy axis, any point where it can land up, so that there is a free energy change which is negative, but that is also not there. So, that means from A to B, as I go from pure A to, as we mix up B, we see that the solutions at each point over A when it goes towards B. Remember, I do not know where this B is, we will come to that B point later, but at least along that line, if I go along that line, I see that B content is increasing, and all those points till it reaches B, we can have a situation like those are all unsaturated solutions, and all of them will be stable. Okay. Why? Because beyond B, if we go beyond B or beyond C towards left side and beyond B towards right side, a peculiarity would arrive at. Let me just see what will be the speciality of B and C. If I take tangent at every point of that delta G mix versus x b plot, I keep having tangent at all the points, keep having tangents, and we will see that B and C, if we do a tangent here, let us say I do a tangent at B, this B tangent will pass through C point, and I am marking those B and C on that delta G mix plot in such a fashion that B and C would be falling on a common tangent between those 2 points. Okay. So, that is a common tangent. So, that is what, when it happens like this, so the B and C in between we have common tangent. So, that case, at least for the time being, I am just giving an intimation that since B and C are part of the common tangent, then I can definitely say A to B, any composition you take, those compositions will be stable, because that composition has no reference to go to when there would be the reference to no point in the free energy regime to go to, so that there is a free energy change which is negative. So, that means it should stay there. Okay. Now, similarly, if I take D to C, if I take that, and C is part of the common tangent which is passing through B also. So, then solutions at each point over D to C, their A content is increasing, and then this can be said that unsaturated solution and all those all are stable, because the same logic we can the what we have put it in this case A to B, same thing, but here unsaturated solution is with respect to B. So, with respect to addition of B in A, but here it is with respect to addition of A in B. Please understand this, this is very important term. So, we see that, and if I try to zoom this particular part, CD part, the zoom portion would look like this. Okay. And you see, at any point if I see, I cannot go upward because there will be positive delta G. It cannot go down also because there are no points where it can reach free energy of that particular solution. So, it will stay there. So, we have understood two extreme ends. Now, let us see what happens between B to C. Okay. So, B to C, I can take one point till this inflection point or spinodal point. Let us say I take this point and another point is this. Let us say this is P, this is Q. So, if I take P and Q, let me just draw it separately here. So, let me draw that same plot here again. Okay. So, this point is midpoint in the composition axis, this is x b, this is 0 0 and this is delta G mix as a function of x b equal to 1 or x a equal to 1 in the composition axis, and this 0 is nothing but the free energy values. We have seen there are 4 points A, B, C, D, and then there are 2 inflection points. Let us say inflection points are M and N, and we are taking a composition in between B and inflection point. Let us say this is P and this is Q. Now, if I draw that P, this particular plot, this particular portion, as well as this particular portion, let us see what is happening there, and there will be a common tangent. And here we have this particular portion is delta G bar M B with composition B, delta G bar m with composition C of B. So, this particular portion is basically delta G bar m of A composition B, delta G bar m of composition C of A. Okay. That common tangent rule we apply. Now, if I draw this particular plot around P, so let us see how it looks like. So, the plot would be like this. So, now this is the common tangent passing through B and C, and this is the Q, this is the P. And now, if I see that, let us say there is an increase in free energy, the free energy is increasing. So, I can have a situation like this composition and this composition. Now, whether the system can break into these two composition, it cannot, because I see that when it happens this way, P to P and it is moving upward, delta G is positive. So, it is not possible. Now, the P can, from P the free energy can go down, and it can go down all the way to the common tangent, and once it reaches to common tangent, it will attain equilibrium, and the free energy change would be given by delta G. So, delta G, and we can write here from P to common tangent which is connecting B and C. Okay. So, that means this will go there, and then it will system would not find any other place to go there, because from below that it cannot reach. So, it will stay there and it will break into a two solutions. So, solution, or we can say homogeneous solution of composition B plus homogeneous solution of composition C. So, this can happen because it reaches equilibrium and there is a spontaneity since delta G equal to negative. So, spontaneously that composition will break into two solution B and C. So, similarly, if I take Q, so this is one part with reference to P. So, if I take Q, same thing can be drawn. I can have a zoom version like this. So, this is C point and we have a common tangent, and this from Q it can go down. So, from here it can go down like this and it will reach to the common tangent, and again composition P. So, it is basically solution Q will break into two homogeneous solution C and homogeneous solution of B, and in this case it is a solution of composition P. And why? Because delta G when free energy change Q to common tangent of BC. So, and this delta G is also negative, and in fact, it cannot go up, because if it does that, so the free energy has to go up. So, from here free energy has to go up to break into two compositions. So, this case delta G of this is positive. So, this is not a feasible solution, feasible transformations. So, the transformation can only happen if we take composition between B to M as well as N to C. All those composition will break into two parts and two homogeneous solutions will be in equilibrium, and since they are falling on a common tangent, and they will break into solution of composition B and solution of composition C. Now, as we go from P and then if we move up, so if I take different composition, we will see that the weight fraction of solution of composition B and weight fraction of solution of composition C will vary, okay, but the composition would remain same. So, if I increase if the composition is increased from with reference to P. So, in this case weight fraction of solution of composition B and solution of composition C will vary, but the composition would remain B and C. Similar happens here, similar thing happens composition Q, weight fraction of solution B, solution C will vary, but the composition of solution that will come out from composition Q would be B and C. Composition will not change. So, those are important aspects to it, and let us see if I can explain from free energy point of view or the molar partial quantity point of view. Now, we know that for equilibrium to establish between two solutions, here remember we are actually making two phases. Why? The compositions are different, okay? Though they are falling on the same del H mix, del G mix versus composition plot. So, that is what here we are actually making two solutions, one is composition B, one is composition C. So, the equilibrium condition is we have to take it in terms of molar partial Gibbs free energy of A in composition solution B and molar partial Gibbs free energy of the same component in the other phase. So, we can write A of, we are breaking into two phases B and C, should be equal to G prime G bar A composition C. So, this particular plot we can actually, these 2 points can be expressed in other forms. Why? Let us say I take a solid solution. So, these 2 points and the temperature I am taking, temperature is below TMA and below TMB. So, both cases I can assign the free energy of pure metal as 0. So, this is G B naught of solid and this point can be G naught of A solid. So, G 1 equal to X A G 1 X A G A naught solid plus X B G B naught solid. So, it should be 0. So, then G 2 is nothing but G 1 plus delta G mix is nothing but delta G mix. Why? Because these two are assigned as 0, because when we have such situation, the solid A and solid B both will be stable. And how do we know that? We have done it before. So, this is G, this is T, this is for TM B, and this is G B naught solid, this is G B naught liquid, and another one which is for A, I can write this. So, this is T M A and this is G A naught solid, and this particular line is G A naught liquid. Okay. Fine. So, that way if I take a temperature here, so that case I can easily assign the pure solid free energy to be 0. So, this line itself becomes G 2 of solid. Okay. So, then I can, this point can be written as G B bar of composition C, and we can write this one as also G B bar of composition B, and we see they are coinciding at the same point. I make this relation as this. So, similarly, at this location I can put a condition like G A bar of composition B should be equal to G A bar of composition C. So, we see that the common tangent we have equilibrium. So, this is equilibrium, this is also equilibrium. Fine. And hence, so this I can write. Now, we can, so it can be written as G A of solid, because it is a molar partial gives free energy of A in solution B would be equal to R T ln A of A in B should be equal to G A naught solid plus R T ln A of composition B, composition C. Now, these two are same. So, I can write R T ln A B equal to R T ln A C. B and C are basically two solutions. So, I can write A B equal to A C. So, I see that even with activity we can relate the equilibrium. Equilibrium condition. In fact, I see that delta G bar M of A in solution B is also equal to delta G bar M of A in solution C. So, we get the same thing here, okay, and those two are also equal. So, now this is one condition. On the other hand, we can write with respect to G B bar of B equal to G bar of B of C, the solution C. So, this would yield similar if we go A B of solution, the activity of B in solution B should be equal to activity of B in solution C. So, this is another condition we are getting. This is also equilibrium conditions. So, those two equilibrium conditions we are getting. Now, what happens? So, I could see that from M to B or N to C, all compositions will break into two phases with solution of composition B and solution of composition C. Now, what happens in between this spinodal? This spinodal, this is interesting part, as we have indicated before, so from here any point you take, let us say I am taking this point, there will be always lowering of free energy if there is a little fluctuation in composition in the system of that solution. This solution, let us say I am taking this solution as S. That solution, if there is a little fluctuation in the composition, that will break into two phases, because there is a spontaneous free energy change. That means free energy change is negative here in this case. So, the S will break into two phases of this composition and this composition. Now, as we go down, it can go down like this. Okay. As we go down, every time I see that the free energy change is negative. So, that means every time there would be a segregation. The A side, one side will be A rich, one side would be B rich. Gradually that will form, and that will again come down below M and N, and then again it will fall back to B C. So, it will segregate into two phases B and C. One side would be A rich, one side would be C rich. Now, interestingly come back to del H mix. Del H mix is positive. What does it mean? A would like to have A type atoms around its surrounding, and B would like to have the B type atom around its surrounding. So, AA bond and BB bond are the most feasible situation when delta G mix is highly positive. Okay. So, in this case there will be always two terminal solutions, I can say composition B and C, of A rich site and B rich site. So, we are actually getting a separation of compositions. This separation of composition, it happens because delta H mix is highly positive, and it leads to AA type and BB type bonds to form, preferably. And it would lead to a separation in composition, and it actually goes towards pure side, and the final composition will be decided by final composition of two terminal compositions, final terminal solution by common tangent, and this entire thing is basically the one single phase is breaking into two phases of two different compositions, and those are actually solutions. So, that is called phase separation. Fine. So, this phase separation is arising because of this particular condition, but if this is small negative, small positive, but that case the plot becomes, delta G mix plot becomes like this. This is delta G mix plot, this is x b 1, this is x b equal to 0, and these 2 points are 0 0, and every time I see that the two composition, if we take, when we mix them together, they will actually form another single phase, or any solution, if I take one single solution will take, it will stay there, because it cannot go below or up, because it is not finding any free energy line where it can reduce its free energy. Okay, the system can reduce its free energy. So, in this case single phase solution. So, finally, I see that what type of phases will be coming out. Now, let us understand that again. Okay, this was the plot A, B, C, D. Okay. I could see that phases, equilibrium phases composition from A to B, and then we have B to C, and then composition C to D. And in this case, so here we have solution of B plus solution C, but here all the points over this AB free energy line or delta G mix line would be stable, and similarly here all the points over this CD line will be stable. So, if I try to see the equilibrium phases over the entire composition range x b equal to 0 to x b equal to 1, and here it is the space where it is talking about pressure, temperature and composition, because I have kept temperature and pressure constant. So, in this equilibrium space the phases will be A, B, C, D. Okay. So, this would be my equilibrium states of all the phases on temperature, pressure and composition space. So, at least we understand that what phases will be stable when we have a situation when del H mix is highly positive. So, we have understood all 4 cases, case 1, case 2, case 3, case 4, and those cases are indicated here. So, indicated here. So, now you understand that how to decide the stability of a phase when we look at free energy versus composition plot. So, now onward we will step towards looking at phase diagram, because the phase diagram is nothing but the graphical representation of different phases as per their stability. So, in case of ideal solutions, things were straightforward, but in case of non-ideal system we have conditions like del H mix is highly positive, del H mix is less positive, del H mix is less negative, or del H mix could be highly negative, and all those 4 cases we have to look at that free energy composition diagram and check for equilibrium condition as per the common tangent and see what phases would become stable, and those compositions will be plotted over a particular isothermal temperature, and that would lead us to a phase diagram when we have non-ideal solutions. So, let me stop here. Thank you very much.